Today we want to start with this standard physics problem wherein we decompose a force into horizontal and vertical components. Or we could think of this as a trig problem where we find the opposites and adjacent, the other way around, adjacent and opposite sides of a right triangle with a 40-degree angle and a 300 Newton hypotenuse. So if we just remember this, since this is a right triangle, we can use cosine and sine. And the horizontal is the adjacent. So the cosine of 40 is adjacent over hypotenuse. So the adjacent, in this case, the horizontal component of the force, will be 300 times the cosine of 40 degrees. So we just grab our calculating machine, make sure it's not directly under a light. And 300 cosine of 40 degrees is 229.8. It says to round our answer to 3 significant figures, so we'll call that 230 newtons. Then we're going to notice that I forgot how to make sure that this ending 0 is significant. How do we indicate this is significant? But then I'll quickly remember we're in a math class. We'll just say that it is. I just needed to have you round off somewhere. I also said show your calculations, and that just means type what you're going to type into your calculating machine. That's all. That's kind of where show your calculations goes with problems that we could just remember how to do. Remember, the point of being in a math class is not having to do all the math all the time. You don't want to write every step. You don't want to write down all 4 products in 23 times 17. You just want to say it's 391. That's like the point of being in the math class, is to not show those steps. And the vertical component just uses sine. We can do the same kind of thinking, or we could just remember that the vertical component is 300 times the sine of 40 degrees. So 300 sine of 40. There we go. 192.8, which will round to 3 significant figures at 193. Any questions? So there is a question. The question is, what's this have to do with the dot product? So if you recall, the dot product is our current project, because 2 days ago we introduced vectors. Yesterday, we started talking about the operations that we can perform on vectors. And one of those operations is the dot product. This is a scalar product of 2 vectors. So the game with the dot product is we take a vector, dot another vector, and that gives us a scalar. Then this raises the question, what is this scalar? Just like a math class, to partially answer a question, that just raises more questions. That brings more answers, that raises more questions, that brings more answers, that raises more questions. Math is like a child that's like, oh, why? 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 until you get to the end of your instructor's knowledge, and then, I don't know. So the dot product is a scalar product. We take a vector, dot a vector, come up with a scalar. You want to know what that scalar represents. Recall that we can find the dot product by finding the sum of the products of the corresponding components. One way to calculate the dot product is the sum of the products of the corresponding components. It's the sum of the products of the corresponding components. So if I have, let's say, V1, V2, V3 is one of my vectors, and my other vector is U1, U2, U3. I just do V1 times U1. That's just plain old scalar multiplication. That's just a scalar times a scalar, product of the corresponding components. V2, U2, V3, U3. The sum of the products of the corresponding components. Remember, even though this V1, V2, V3 is a vector, so V1, V2, V3 make up a vector. V1, V2, and V3 are all scalars. So they're scalar components of the vector V. So here I have V dot U is this sum of these products. But right before I said that, I said one way to calculate a dot product is to find the sum of the products of corresponding components. But just like skywalkers, there is another, and another, and another, and another. It's more of a soap opera, is what I'm saying. Star Wars is a soap opera. And when you're watching Star Wars, adventurous as it may be, you're watching your stories. Soap opera. Didn't have to be that way, George. And Disney. I'm still waiting to be bought out by Disney. So I don't know, we just seem to be buying everything. There's another way to calculate the dot product. So the other way to calculate the dot product is to say that V dot U is the magnitude of V times the magnitude of U times the cosine of the angle between them. Magnitude of V dot magnitude of U, magnitude of V times the magnitude of U times the cosine of theta. So notice that the magnitude of the vectors are both scalars. Cosine of theta is a scalar, so we are ending up with a scalar product. Like we're supposed to. Vector dot vector equals scalar. In this case, we would need to know the angle between the vectors. If I just list the components of V and the components of U, we don't know what the angle is. But more importantly, we can use this to find the angle between two vectors. So that's the big deal here. We can use this to find the angle between vectors. So here we have two vectors in R3, 5, 3, -2, and -4, 0, 1. And I want to find the angle between these two vectors. So the pieces that we'll need are v dot u, the magnitude of v, the magnitude of u, and then we can use that to find the cosine of the angle between them. And then we'll just cosine inverse. If we think about cosine inverse will give us an angle between 0 and 180. So that's good. We're not going to have to worry about this first and fourth quadrant business with sine. Cosine will tell us about the first and second quadrant. So much better. So let's start gathering our pieces. I need to know the magnitude of v. That'll be the square root of 5 squared, 3 squared, and -2 squared. So 25, 34, 38. Did I do that right? It's arithmetic. It's early, and I'm not always careful with my arithmetic. So no objections. Motion carries. It's 38, square root of 38. You can't vote on this stuff, but we just did. There's precedent for it. I can't remember what state it was, but at one point a state had legislated that pi was equal to 3. And it said, by law, pi is equal to 3. I can't remember what state it was, but you can probably guess the region of the country that came from.
Probably Florida.
I bet it was California. That would have been hilarious. So we also need the magnitude of u. We need a lot of parts here. 3 whole parts. It's ridiculous. Instead of just 2. So we got a -4 squared plus 0 squared plus 1 squared. So is that 17? No, it's the square root of 17. I apologize. That was a leading question. There weren't any points on the line. Not a big deal. And we need the dot product. I just noticed that I think yesterday the -2 was a +2, so I can't use the dot product from yesterday. So let's calculate the dot product. So 5 times -4 plus 3 times 0 plus -2 times 1. So -20 minus 2, -22. So we can take our dot product and solve for theta. So now theta will be cosine inverse of v dot u over magnitude of v times magnitude of u. So I'm going to divide by both of these magnitudes and then do a cosine inverse. So take the -22, divide by the 2 magnitudes. Put your parentheses in the right place. Dividing single line syntax. Cosine inverse, a -22 divided by a square root of 38. Close the square root times the square root of 17. Make sure we close our square roots if we're talking to our Texas Instrument style calculating machine. And then we can close the cosine inverse. And then, oh no, then we can close the denominator. And then we can close the cosine inverse. 1, 2, 3. And let's round to the nearest degree, even though I didn't specify earlier. So 150 degrees. Oh, once again, is there a way to make that 0 look significant? Is there like some kind of standard, or we just have to know?
Do you put a decimal?
You just put 150 and then put a decimal, and that says that 0 is significant. I like that. That's kind of cool because it's simple. And you're like all one. So if you're like all 150, and it's like, oh, is that 2 or 3? But if you do this, does that make it 3? I like that suggestion anyway. So, new rule. Also, I like 150. It's got a 30-degree reference angle. That was my original angle for the opening problem, but I switched to 40 because there were too many 3s running around. And then when I realized I needed to pull out my calculator to do the calculations, like, oh, I know sine of 30 and cosine of 30, but I don't know sine and cosine of 40. I'm like, oh, I should have gone with 400 newtons. So then I could have just taken the numbers that I know, sine 30, cosine 30, and multiplied by 400. This is what happens when I have 8 o'clock class. I make poor decisions like that. So the way to think about this 150-degree angle is to notice that we do have 2 vectors going off in weirdo directions in R3. But if we only have 2 vectors, 2 non-collinear vectors, then they are sitting in a plane. So whatever weird angles, whatever weird directions these vectors are going at, we can always orient ourselves so we're looking straight down at them in the plane at the plane in which they sit. So we can imagine here's our vector v. Then 150 degrees off of that is our vector u. There's the 150-degree angle that we just found. So look at v and u from above the plane in which they sit, and we can see that angle. So 2 non-collinear vectors will define a plane. We're just taking a top-down view of that plane. Question? So we got this dot product. That's the dot product. We got 2 ways of calculating this dot product. I still haven't told you what this scalar means. Hopefully this is not Game of Thrones, where I film something alluding to some kind of payoff later, where I'll tell you what the dot product, that scalar from the dot product represents, and then just never tell you because I get bored doing this show and want to end it. Has there ever been a pop culture phenomenon that disappeared from the pop culture as quickly as Game of Thrones. We all just canceled that so fast. Like, we still talk about Star Wars. There's been like a good Star Wars movie. Maybe two. And it's still just like everywhere. Game of Thrones, man, we've all let it go. It's like, oh no. And I think the showrunners that did that to us, they still get to work. You know what I mean? It's like we got rid of Game of Thrones, but they're still allowed to make stuff. I mean, guys, if you're bored with the show and you don't want to do it anymore, just hand it off to someone else. Just don't let it be J.J. Abrams, because there's only so much lens flare I can look at. You know what I mean? I don't really care if you don't tell us what's going on in your movie. That's fine. But I want to know that you know. I need to know that you know that you're not just making stuff up. You know what I mean? Like, there are a lot of mysteries that my players have not uncovered in my D&D campaign. I know what's going on. They don't. They have to figure it out. It's okay for them to not know. It's not okay for me to not know. J.J. Abrams completely misses the point of his mystery box. It's fun for the audience to wonder what's inside. But you got to know. You don't get to participate in that fun. I don't get to participate in the discovery. I have to know. My fun has to come from other people discovering or other people wondering. Full disclosure, as a DM, every third mystery, I won't know, but I will be listening to your speculation. And you're like, well, what if it's this? And I'll just listen to your conversation, and then I'll pick my favorite. Actually, what I'll do is I'll pick your favorite. And we'll be like, oh, wow, maybe that's it. And I'll be like, oh, yeah, good job. You figured that out. And then just reveal that at a later time. They'll be like, oh, yes, we knew it. And they all high-five each other. You know what I mean? Maybe I didn't know at the time, but I did know eventually. You can't just be like, oh, I don't know what's going on in the mystery box. It's your story, dude. Come up with something. And don't just make it copy and paste the previous one. You know what I mean? Anyway. Now, if you are a J.J. Abrams fan, it's very easy to level at me. It's like, oh, well, why don't you do better? It's like, well, I admit that I can't make a better movie. But you know what? That's not my job. You can go watch I can't think of a bad football player because I stopped watching football and baseball. You can say, you can observe a quarterback that is objectively bad at his job without having to be a good quarterback. You don't have to be Peyton Manning to say, man, this guy is a bad quarterback. Peyton Manning is a good quarterback, I think, right? I can't remember. Anyway. I know why I remember Peyton Manning. It just occurred to me. He made those commercials where he's a bully. Because they had like noodly arms Peyton Manning, and he was making fun of noodly arms Peyton Manning because he had noodly arms. That's not okay. You don't just bully people for things like that. The first one where it was like that series of commercials where it was creepy Rob Lowe, that one he should be made fun of because his actions are bad. He's being creepy, and that needs to be called out. But other ones, it's like, all just you're making fun of him for things that they don't really have control over. You know what I mean? Anyway. This one's for you, Peyton Manning. Nice nose. See? It's not cool. That's just the way his nose looks. Not okay to make fun of his nose for that. Anyway, I digress. I'm acting like I don't want to tell you what the dot product represents, but really, we got down to the bottom of the page, and I'm relishing the fact that I've used all 8 of my pens on this one. So let's move on. I solved this mystery. If you remember this day, last week on Tuesday, and my pens weren't working, that's because they were the wrong pens. And so now I've kind of wrecked 2 pages of my notebook. All right. That was 3 digressions. So we've already seen that one of the things that the dot product will tell us is the angle between vectors. That is useful. The other thing it tells us is how much of one vector is going in the direction of the other vector. The component, so v dot u will tell us the component of v in the direction of u. Oops. And vice versa. It can tell us the component of u in the direction of v. This is a generalized version of the horizontal and vertical components that we calculated at the beginning. So think of this as a generalized version of horizontal and vertical components. Replace your horizontal component instead of horizontal and vertical. Replace horizontal component with a direction u or v. So it's going to be the projection of v onto u. It'll tell us how big is the projection of v onto u. The reason I picked horizontal is because the second definition of the dot product, magnitude of v times the magnitude of u times the cosine of the angle. Cosine was related to the horizontal one. Told you I eventually get lazy about norms. Just like a math teacher, clarify then make it worse. So recall that this is what we did. We said, first of all, we dropped our lengths, our magnitudes. The reason that we dropped our magnitudes from FH was that we said this is in the horizontal direction. We've included that information. We just need to know how much is there. And so we just took the magnitude of F times the cosine of theta. And in this case, the direction was encased in that horizontal part, where the direction, the horizontal direction, is going to be described by a unit vector, a horizontal, the unit vector. So here, the direction a unit vector that's horizontal. How's everybody okay? So we got some stuff to sort out here because there's some stuff missing. I've got this magnitude of the horizontal component. I got the magnitude of F. I've got the cosine of theta. Where's the dot product in all this? Where's the 1, 0 in all this? Let's go back and think about it. Oops. I got overzealous with my norms. Oops. So the question is, our horizontal vector was magnitude of F times the cosine of theta And we know that this is going in the horizontal direction because it's FH, because we were just doing horizontal and vertical components. But this is a component of the vector. How much is going in this direction? But I've said that this is related to what we're writing down here with this dot product business. So where is this dot product business going to be? Where does the direction show up? Sorry, internal debate. Where does the direction show up? How does the dot product enter into it? We see sticking out at the end that cosine of theta. So there's some extra business going on over here that we need to figure out. Good question. So right now, if I explain how all this works, it'll make calculus very simple. And it'll be instantly clear how the dot product tells us about components of one vector in the direction of the other vector. But I have to do it right now. If I delay at all, then we're going to have to go through calculus at the normal rate. And we're going to get stuck on stuff and be confused instead of just instantly understanding it the same way that I understand it, which isn't perfect, but further along. But I have to do it right now. If I don't do it right now, then it's just going to be, we're just going to have to struggle like normal. So all we need to do to completely understand Calc 3 in this instant is, oh, darn, look at the time. I guess we'll have to wait until tomorrow. That's going to do it for today. Figure out what the connection is between these two statements. And we'll talk about it some more tomorrow along with the cross product. That's going to do it for today. I will see y'all on tomorrow. Everybody have a good day, and thanks for playing.